In lesson 27, we talked about the relationship between force and depth when there were no surface forces, meaning as the tip and sample come into contact, there's no force, but when contact is established, the force goes as the 3/2 power of the indentation depth. And this, of course, is for a sphere and a flat in the assumptions that I listed in lesson 27. Frequently, however, there are surface forces. Most of the time those are attractive. So the first thing that you might think about doing is saying, okay, I'll have surface forces 0 when tip and sample are far away, but becoming increasingly negative until contact is established. And then after contact, I'll have the same basic shape here. So what this implies is that the tip and sample don't noticeably deform due to surface forces. That same shape as the Hertz mechanics in white just gets shifted down, and you add perhaps a van der Waals interaction. The problem, however, comes in this area down here. That's a discontinuity in slope, and I have never seen that in experiment other than discontinuities in the sense of instabilities. So this might work for very, very stiff materials where the actual shape might be very close to this, but frequently, well, most of the time, I see a gentler transition between the purely attractive and the net repulsive regimes. The next thing you might think about doing is saying, okay, let's assume that I have no surface forces. I'm coming along and about to make contact, and then when I do make contact, I've got a fairly strong immediate chemical-like interaction, and then I load and unload, and as I pull tip and sample apart, I'm stretching the chemical bonds at the surface, and I'm forming an adhesive neck that suddenly rip apart. So here we have a hysteresis loop due to adhesion of the surfaces of the tip and the sample. This approach works well for compliant materials that have large work of adhesion and large tip radius. But since most AFM experiments are done with small tips, this set of assumptions has limited applicability. What we'd really like is a set of assumptions that would lead to a smooth transition between the purely attractive regime and the net repulsive regime. And furthermore, if that could be not too mathematically complicated, that would be good for purposes of learning and understanding. Let's start again. Here's another sketch of the Hertz equation. And let's assume the following set of circumstances. That the cantilever is stiff enough, there are no instabilities at the cantilever, and the sample is acting on the tip, so the cantilever bends forward, and whatever attractive forces there are acting on the tip from the sample, by Newton's third law, the tip acts on the sample, and so if the sample is compliant and the work of adhesion is strong enough, then the sample bulges out from the nominal surface position, which would be the y-axis here, to greet the tip, if you will. And as those outermost atoms are coming into contact, the attractive force still grows because the tip is getting nearer and nearer to the bulk, the semi-infinite half-space of the sample. And then, as you would expect, the repulsive forces start to grow, and the sample turns around. Rather, the cantilever turns around. Let's make sketches of what's happening at various points. Here would be where tip and sample first make contact. The sample's bulging out, like this. Here, this would be where the tip has indented such that it has come back to the nominal surface position. And here, this is where the cantilever is applying no force, and the indentation depth is due to surface forces alone. How do we write the equations for that? Well, certainly in the limit of no surface forces, we would want to return to this same equation that is up here in the upper left, Hertz equation. And remember, we can also write this as reduced modulus contact radius cubed over tip radius. So let's put that as our first term for our new situation with surface forces. So that's an easy part. And another easy part is to say that up to this point, where the first atoms touch each other, we'll call that delta zero. To the right of this point, we have attractive forces only. And so if you remember back to lesson 25, we said that van der Waals attractive forces can be written as minus 2 pi tip radius work of adhesion delta 0 over delta quantity squared. Now you notice I left a factor of 2 out. That's on purpose. It's not a little boo-boo. And I can come back and justify that at a later time. Once you're to the left of contact, then you would still have this amount of attractive force, which is minus pi tip radius work of adhesion. And so that will be our third term in our equation that we're building here at the bottom. And what's interesting is the term that we're going to put in the middle. The term in the middle has to account for how attractive forces continue to grow after the first atoms on the tip in the sample have already started to touch. What's happening is that the tip is coming closer to the semi-infinite half-space of the sample. At the same time, it's touching the little bulge of the sample. You can write this as minus a big long square root now, 3 pi work of adhesion reduced modulus contact radius cubed all over 2. There's just one more thing to adjust now. You remember for Hertz, we had a relationship that a squared is approximately equal to tip radius times depth, or other words, a is approximately equal to r times the root of depth. And this would be absolute value here. And so you would get something like that for A for Hertz. Well, if we did the same thing with our new equation, we would be saying, well, there's no contact radius even though tip and sample have come into contact at delta 0. So we need a modified expression for A. Our new expression for A is A squared is approximately equal to R times quantity delta 0 minus delta. Phew, this slide is full of equations and sketches. Let's now see if we can find some meaning in this equation at the bottom. Here is a series of computer-generated force curves for increasing reduced modulus, and the axes are force and separation or penetration depth. Here, this is the direction of increasing reduced modulus. So the higher the modulus, the more the cantilever bends backwards for a given depth. What's interesting to me is that this also happens on the right-hand side of the plot, but now the orientation of the increased force is different. These points along this level corresponds to minus pi tip radius work of adhesion. These are the points where the tip and sample first come into contact. A more compliant material bulges farther out for the same work of adhesion than the stiffer material. So on this side of the plot, this is the direction of the increased reduced modulus. Now here we have a set of curves that have different work of adhesion. You can see right away that the direction of higher work of adhesion is this way because the cantilever bends farther forward for the higher works of adhesion. And what I'd like you to notice here is how the minima are arranged not vertically down from the origin, but off to the right. So this, once again, is indicating the bulging out of the sample for higher works of adhesion. And finally, here we have a set of 5 curves where I've varied the tip radius. And what I think is interesting here is the opposite effects. Here this is increasing tip radius, making the contact stiffer. And here this direction is increasing tip radius, meaning there's more material to be attracted between the tip and the sample during the initial stages of contact. In summary, here's the set of equations about which we've been speaking. I have not yet introduced the last equation, delta 0, the amount that the sample bulges out towards the tip. It is greater for greater tip radii, work of adhesion, and smaller reduced modulus. This system of equations we call BCP contact mechanics, after myself, Nancy Burnham. My collaborators at the time were Richard Colton and Hubert Pollack. I use BCP contact mechanics to get started. It's a good estimate. It is simple, not as sophisticated as other alternatives, but the alternatives tend to have parametric equations or fourth-order roots. This makes computation rather slow. If I'm simulating a dynamic force curve where the tip touches the sample hundreds of thousands of times a second, I want my initial calculations to be fast, yet representative of the basic physics.